Hello, my name is Alex Cunliffe. Thank you for joining me today. This is the second part of a two-part series where I'll be talking about model compression for deep learning models. In the first part of the series, I covered serialization and quantization and the effect that it can have on the performance of a model at inference time. If you want more details about any of this, definitely check out our blog on Prolego.com blog post, and then also check out the GitHub repo where it has code samples so you can try some of this out for yourself. So like I said, I covered serialization and quantization in the last video. In this one, I'll be talking about two other methods for compressing models. The first one is pruning, and the second one is changes to model architecture. So for pruning, we're talking about when these deep learning, especially these large deep learning models, they can have millions to even trillions of parameters. And so it would make sense that maybe not all of these parameters are equally important at inference time. And if we want to reduce the size or increase the speed of a model, it might be a good practice to discard unimportant weights. So this begs the question, well, how do you even know if a weight is unimportant? And there's a few different pruning approaches, and they address this question in different ways. The first approach for pruning is called magnitude pruning. And for this approach, you're simply looking at the absolute value of weights, and weights with high absolute value are contributing more to model predictions than weights of low absolute value. And so it would be reasonable to say that you can discard or zero out those low absolute value weights. Magnitude pruning is going to work better in a situation where you are training a model from scratch. However, with the advent of self-supervision and transfer learning, I think it's much more common now to start with some sort of a base model that's been trained on one data set, on one task, and then do transfer learning whereby you are continuing model training on potentially a different data set or a different task, already using the knowledge that's been learned by that pre-trained model. Now, in that scenario, the weights in your final model are going to be related both to the importance of or performance on the task at hand that you're working on, but also the performance on the original task that the model was pre-trained on. So you can't necessarily rely on magnitude pruning for transfer learning. In that scenario, movement pruning might make more sense, where instead of looking at the absolute value of weights, you were looking at how the absolute values change over the course of training. And weights that decrease very much during training, those are weights that are likely unimportant or even counterproductive to your task at hand, and those can be discarded. A third type of pruning is more transformer specific, and it's pruning attention heads. So for transformer architectures, they have these parallel attention heads that allow the model to focus on different aspects of a sentence or a context in order to make a prediction. And this paper that was published in 2019, Are 16 Heads Really Better Than One, demonstrates that many of the attention heads that were used during training can be pruned at inference time without significantly affecting model metrics. And it's just a matter of identifying attention heads that are important contributors versus less important contributors and removing those less important attention heads. And so we're going to try that now. We're going to start with our a base Roberta transformers model, and we're going to sequentially prune attention heads. First 25%, then 50%, then 90% of attention heads, and then profile memory in order to measure disk space, runtime, and memory usage. So I'm showing that here. We have our baseline model, and then prune 25, 50, and 90%. And you can see for this model, especially the hard disk space has decreased as we do model pruning. And then also inference time is decreasing from 20 seconds for this particular task and data set down to 12 seconds. So you might also ask, shifting gears a little bit, well, if we really want our model to be more lightweight or faster, why not use just a smaller model? And that's a very legitimate idea. The question that you would have to ask then is, well, a lot of times we use these larger models because they improve the performance on the task at hand. And so one way to kind of get the best of both worlds is through an approach called model distillation. So during model distillation, you are taking a larger teacher model and you are training a smaller architecture, a student model, to behave like the teacher model. And so to behave like the teacher model, that means not only doing well at the task that the teacher model has been trained on, but also you add in some terms to the loss function that are enforcing. You want the student model to mimic the behavior of the teacher model. So through the loss function, you are encouraging the model to yield similar intermediate and also final results as the teacher model. So kind of thinking about this conceptually, you're thinking, I don't just want my student to behave the same way as the teacher, I also want it to go through the same thought processes as my teacher model in order to arrive at a final prediction. So we're going to test a distilled version of the Roberta model and see the effects on memory, latency, and so on. And you can see that by using the smaller model architecture, we've been able to reduce kind of across the board RAM consumption, hard disk space, and also inference time. So now, taking what we've learned from both the first and second part of this series, let's put it all together. And I think generally, so let's take what we learned from the last series and also this one and put it all together. If you're looking to apply model compression, I generally recommend applying the things that we've talked about in the following priority order. So first off, you're going to get the biggest gains for the amount of work that you put into model compression by simply using a library like ONNX in order to do serialization followed by quantization. And already we saw from the last video that for some of, for the application we were testing, we were getting an order of magnitude speed up nearly, as well as reducing the size of the model and the memory consumption. If you're trying to eke out some additional performance gains, a next place to step would be to use a smaller architecture, such as distill Roberta, or use a distillation technique as part of training. And then additionally, if you're still trying to eke out further improvements, prune attention head. And so when we put it all together, we can see what we get here. We started with our baseline Roberta model, inference time of 20 seconds, hard disk space of half a gig. And through applying all of these steps sequentially, get down to an inference time of only 1 second, significantly reducing all of the other performance metrics that we were measuring. So that's all I got for you. I hope you've learned from this video about how you can apply model compression in order to speed up your models during inference time and make them a little bit more lightweight. Thanks and happy modeling.